Hello and welcome to this video lesson on halide ions with specification reference 3.2.3.1. To start with, let's see what we want to learn in this video lesson. Firstly, we want to be able to explain the trend in reducing ability. And I hear you say reducing ability. Oh, I thought they were oxidizing agents. Okay, we'll explain that. So secondly, we want to know the different products formed by the reaction of a sodium halide, X is the halide, and sulfuric acid. And we want to explain why acidified silver nitrate is used to distinguish between the halides. If there was a bunch of halides and you didn't know which particular halide it was, you would use the silver nitrate test. And you would also want to know why it's acidified. Also, we're going to analyze the trend in solubility of the silver halides in ammonia, because we use ammonia to check the previous test, the silver nitrate test. And lastly, we want to prepare for required practical 4, because the first part to required practical 4 is the silver nitrate test, distinguishing between various halides. So this slide's on halide ion formation and oxidation, and we're going to do this just in preparation to looking at the trend in the reducing ability of the halide ions. So let's go back to the chemistry basics and look at chlorine, for example. This is a chlorine atom, and you know it's in group 7, and it wants 1 electron to fill its outer shell. That's what makes it happiest. And so when it does that, when it reacts, you're going to get another electron. Let's draw it here. This is the extra electron that it might get, say, from sodium if it was reacting with sodium. And now it is a chloride ion. So we would draw our square brackets around it and give it a minus charge, because it's taken that extra electron from something. So it's been reduced. So this is the oxidizing agent. Because it wants to take an electron off something. But the chloride ion, and if we use the general term, the halide ion, is going to be a reducing agent. It's going to be a reducing agent, which you remember will reduce something else but get oxidized itself. So if it's going to take part in a redox reaction, if the halide, in this case chloride, is going to take part in an redox reaction, it can't gain another electron because it's already got a full outer shell, so and it's already negative charge. So you know it's not going to gain another electron. If anything is going to happen at all, it's going to lose this electron. So one of the outer electrons, perhaps the one it gained, is going to be lost in a redox reaction, which means that it's a reducing agent. It's lost an electron, so it's been oxidized itself, and it's given that electron to something else. So that's why it's called a reducing agent. So what we're going to do on the next slide is to compare all the halides from chlorine through bromine and iodine, compare their reducing ability, or their reducing power. So that's what we're going to do on this slide. We're going to compare the reducing power of the halides. So let's start off just by reminding ourselves what reducing power is. And reducing power is how easy it is for a halide ion to lose an electron. So how easy it is for a halide to lose an electron, and how easy it is to lose an electron depends upon the attraction between the nucleus. So I'll write this, depends upon or proportional to the attraction between the nucleus and the outer electrons. And that, of course, the attraction between the outer electrons and the nucleus depends itself upon the distance between the outer electrons and the nucleus, the shielding from inner shells of electrons, and also the nuclear charge. The more nuclear charge, the more it's going to be attracted to its outer electrons. Okay, so that's what we're talking about. Let's have a look at the various halides. Actually, we'll start with fluoride. So we've got fluoride. This is a fluorine atom with an extra electron, you see, and it's got its negative charge there. And you can see that what we're going to do is we're going to go through the three factors, distance, shielding, and nuclear charge, that affect the attraction between the nucleus and the outer electrons. And you can see with fluoride, the distance between the nucleus, let's say the nucleus is the F, that distance there is quite small relative to the other halides. So that distance is quite small, and the shielding is quite limited because look, we've only got this one inner shell to shield the outer electrons from the nucleus. And our nuclear charge, well, it's quite small actually, isn't it? Because fluorine's got quite a small nucleus. So that's the three factors for fluoride, and they mean that the reducing power is quite low because it's going to want to hang on to that electron that it's just grabbed off something. Whereas if we look at chloride, then the distance between the nucleus and the outer electrons has increased. All right, so the attraction is going to be less because of that. And the shielding now is shielded now not only by the inner, the 1s shell, but also the second shell of electrons. So it's got quite a bit of shielding as well. So that will further reduce the attraction of the outer electrons to the nucleus. However, the nuclear charge is larger, and so that will increase the attraction between the nucleus and the outer electrons, but not as much as the previous two factors have decreased it. So chloride, Cl-, has a greater reducing power than fluoride. Okay, so that's next one. And then if we look at bromide as well, just to accentuate the trend, distance has increased even further, right? So that's going to reduce the attraction and increase the reducing power. Shielding is even more, so we've got three complete shells of electrons to shield the outer electrons from the positive nuclear charge. So that is going to decrease the attraction between the nucleus and the outer electrons further, and therefore increase the reducing power. However, the nuclear charge in bromide is going to be higher, so that would increase the attraction and decrease the reducing power, but not enough to counteract the previous two factors. So bromide has a greater reducing power than chloride. And so you can see the trend there. The trend is increasing reducing power as you go down the group of halides. And iodine would be even would follow the same trend. It's even bigger and would be the strongest reducing power halide. So that was a theoretical explanation of the reducing power of the halides, i.e. that they increase from fluoride through to iodide in reducing power. But if we wanted to demonstrate that practically, how would we do that? Well, we react them with sulfuric acid. So here we're saying that the varying reducing power of the halides is demonstrated by their reactions with sulfuric acid. So what we're going to do here on this slide first is to do the reaction with sulfuric acid generically. So I'm going to use X to represent any halide. So we're going to start off with sodium halide, NaX, and we're going to react that with some sulfuric acid. And as it happens, that makes sodium hydrogen sulfate and a hydrogen halide. And a hydrogen halide. And let's just note that in green, right, because that's the interesting part of this reaction. A hydrogen halide is produced. Because what happens now with sorry about the dog bark, let's carry on. So this happens with all, this reaction here happens with all halides, but what happens next depends on which halide you have. So some hydrogen halides, that's the hydrogen halides we produced in this first reaction, some of them are strong enough reducing agents to reduce the sulfuric acid further. Right, so let's just highlight the fact that we are reacting a hydrogen halide with the sulfuric acid, and they're strong enough reducing agents that they reduce the sulfuric acid to water and sulfur dioxide, according to this reaction here. So we've got our hydrogen halide, and it reacts with the sulfuric acid still in the reaction mixture, and that's going to make some halogen and sulfur dioxide and water, like that. So I mentioned that the hydrogen halide does the reducing, and it does that to the sulfuric acid, but let's just check that that is the case, in fact, and we're going to check that by looking at the half equations. So the half equations I'll do in a different colour. So the halide half equation first, we've got X minus in our hydrogen halide, we've got two of them from here, and they are making the halogen like that, and in the process they give up 2 electrons. So you can see that the halide has lost electrons, and consequently that means that it is oxidized. So in this process here, the halide X minus is oxidized. Okay, and the other half equation starts off with our, let me do that in a different colour still, go back to black. Right, it starts off with our sulfuric acid. Yeah, and it needs a couple of hydrogens. I won't go through the whole process of doing the half equation, I'll just give it to you. It's the subject of a different video lesson. This is the half equation here, so you get some sulfur dioxide and our 2 water molecules from here and here. So that's our other half equation, and you can see that sulfuric acid is reduced. Sulfuric acid is reduced. You can see that because it's accepting electrons. Good, okay. So that is it for most of the halides where their reactions stop. but for one halide, the one with the most reducing power, that is the iodides, then there's an extra step in the reaction still. So for iodide, your hydrogen iodide reacts with sulfur dioxide here, in a further reaction still, and that is another reduction reaction where the hydrogen iodide reduces the sulfur dioxide further to hydrogen sulfide or sulfur. Okay, according to this reaction here. So I'm writing it HX to be consistent, but actually it's only iodide that that reacts like this, and we need 6 of them, and it's going to react with the sulfur dioxide to make hydrogen sulfide, turning itself into the halogen. I should write that as X2 really. Let me rub that out and write it properly, just to be consistent. So it's making X2 and a couple of water molecules. Okay, and that's where even iodide stops. So in red, just to finalise this slide, I'm going to write how to differentiate. So we've got sodium, we've got the fluoride, and we've got the chloride that only do the top reaction, the first reaction in blue. Bromide will do that reaction, and also the hydrogen bromide will reduce the sulfuric acid further, and the iodide will do not only those two, but the hydrogen iodide will reduce one of the products of that second reaction and reduce that further as the third reaction in blue down there. So that's how we demonstrate and also differentiate between the halides using their reactions with sulfuric acid. So before we go any further, let's see what we've done and what we've still got to do. We've done this explaining the trend in reducing ability. If you remember, we looked at the usual 3 factors: distance from the nucleus, shielding, and nuclear charge. And we used those to explain the trend in reducing ability of the halides. And we've just done the different products formed by the reaction of various halides and sulfuric acid. So just to summarize that for you, remember the fluoride and the chloride. They just did the first step. So the product of that first reaction was sodium hydrogen sulfate and your hydrogen halide. So that will either be your hydrogen fluoride or your hydrogen chloride, depending on which halide you started with. So that is for fluoride and chloride. Now for bromide, we took that first reaction, and the hydrogen bromide reduced sulfuric acid further, such that our products were the halogen bromine and also some sulfur dioxide and some water. So that was for bromine, full stop. And iodide took that sulfur dioxide and reduced that further. So the products of the reaction of iodide with sulfuric acid were hydrogen sulfide, iodine, and water. Okay, and so that's a summary of the previous slide, and allows us to tick that second learning objective. And what we want to do now is go on to testing for halides using the acidified silver nitrate test, and this is going to be the first part of required practical 4. Okay, so we're going to have a look at the silver nitrate test, which is used to distinguish between the halides, because although the halogens are very distinctive in their colours, the halides are all colourless. So they would look like this in a test tube. This could be fluoride, chloride, bromide, or iodide. And they all look the same, so we can't distinguish between them. So what we're going to do is we're going to use the silver nitrate test, sometimes called the acidified silver nitrate test, in order to distinguish between these halides. But first, what we want to do is we want to add some nitric acid, and you add some nitric acid to the halide, add some HNO3 to the halide, and that's to remove impurities. So that our results are true. Here's a little question for you. Why wouldn't you use hydrochloric acid instead of nitric acid? Well, hopefully you spotted the fact that if you used hydrochloric acid, you're adding chloride ions, which might completely muck up your results. So we don't use hydrochloric acid, we use nitric acid, and that just removes the impurities. After we've done that, then we're going to add a few drops of silver nitrate solution. So silver nitrate has a formula AgNO3, because the Ag is a 1 plus ion and the NO3 is a 1 minus ion. And what happens is the silver ion reacts with the halide ion, and sometimes you get a precipitate. So it's like this. You've got Ag plus the halide ion. I'm going to use the generic X for halide. They're both aqueous in solution, and usually you get a precipitate or a solid. So that's what we're going to do, and when you do that, this is what you get. Okay, so you get, depending on which halide it is, you get different looking precipitates. So what we've done is we've taken these 4 samples, 1, 2, 3, 4 samples of each of the halides, and now we've got 4 test tubes, and after we've acidified it, we've added a few drops of silver nitrate, and we've done that for each case. Added a few drops of silver nitrate, give it a shake, and this is what you get. So for fluoride, you don't get a precipitate. You do not get a precipitate. And so that's clear. If you don't get a precipitate, you know that it's fluoride. And for chloride, you get a white precipitate. So this is a white precipitate of AgCl. This white precipitate, and so let's just label it as white. And for the bromide, you get a precipitate of silver bromide, and that's called off-white or cream. Hopefully this photograph is good enough for you to tell the difference between white and cream. And I think you can distinguish the iodide, can't you? This is the precipitate of silver iodide, and that's yellow. That's a yellow precipitate. So now we can distinguish between the halides. Fluoride, if there's no precipitate at all. If it's a white precipitate, you know it's a chloride. You started off with a chloride. If it's a cream or off-white, you know it started off with a bromide. And if it's yellow, you know it's an iodide. Okay, so that could be as far as you go if you're happy with that. But you might not be, because if you look at the 3 test tubes with precipitates, they are quite similar. and it's not like a definitive test, especially the white and the off-white of chloride and bromide. So what you might do is you might do a further test just on the chloride, bromide and iodide, because we're happy with fluoride. We're happy that fluoride is different enough to identify that specifically. But if we wanted to be sure that well, we didn't quite know whether it was white or off-white or cream or yellow, then what you would do is you would do another test using ammonia. So to differentiate between the chloride, bromide and iodide, notice we haven't got the fluoride here, we're using ammonia solution. And this is the same samples from before, and so we're not going to use the fluoride one, but what we are going to do is we're going to take the chloride, yeah, and we're going to add some ammonia to it, or some concentrated ammonia. So that becomes this one. We're going to take the bromide, and that becomes this one once we've added our ammonia to it. And the last one becomes our iodide. And what we're going to do is we're going to add, so both of these are, this is the silver chloride precipitate, and this was silver chloride. The one next to it with the pipette above it was also silver chloride, but we've added dilute ammonia. We've added the dilute ammonia to this silver chloride, and it has, the ammonia has dissolved the silver chloride precipitate, so it's now become clear. Whereas if we were to do that with the bromide and the iodide, then we wouldn't dissolve the precipitate. All right, so if dilute ammonia dissolves your silver halide precipitate, you know that that halide was silver chloride. Okay, so now we've got fluoride sorted out, and now we've got chloride sorted out, but we're still not quite clear about the bromide and the iodide. So what we do is we take the bromide and the iodide and we add concentrated ammonia. We add concentrated ammonia to the, this is the silver bromide precipitate, and this is the silver iodide precipitate. And when you add concentrated ammonia to silver bromide, it does dissolve the silver bromide. But when you add concentrated ammonia to the silver iodide, it doesn't dissolve it. And so now, so if you've taken some, you've got two remaining, it could be either bromide or iodide, you don't know which one. One might look a bit yellowish, but you can't really tell. So you've tried the dilute ammonia test. Now you're going to try the concentrated ammonia test. And if it dissolves, you know it's bromide, and if it doesn't dissolve, you know it's iodide. So basically you have now truly distinguished between each of the halides, and now you know which is which. But we will do one more slide just to summarize those results to help you remember them. So we've got rid of that, and instead we're going to have a little table, and in our table we will have our halide, and we'll have our result from adding ammonia, whether it be dilute or concentrated ammonia. Okay, so we've already sorted out our fluoride, so we don't need to add ammonia to our fluoride, but we do want to distinguish between our chloride, our bromide, and our iodide. So if you remember, when we added dilute ammonia to our chloride, it dissolved. So the precipitate dissolves in dilute ammonia. but the bromide and the iodide don't dissolve in dilute ammonia. So we know which one is our chloride now, but we don't know, we still haven't distinguished between bromide and iodide. So then we add concentrated ammonia, and the concentrated ammonia dissolves the bromide. So here we can say the precipitate dissolves in concentrated ammonia. And let me underline the key word. So that's dilute and that's concentrated. So now you know which one is your bromide. If it dissolves, it's bromide. But just for completion, let's write this: precipitate insoluble for the iodide. The precipitate is insoluble in concentrated ammonia. So again, the key there is insoluble. So now we've differentiated between our iodides. And one last thing is just to summarize our solubility. So our solubility, this is our most soluble, down to our least soluble, in order from chloride to bromide to iodide. So there we have it. That is the silver nitrate test, followed by the ammonia test to distinguish between the halides. And that just leaves us to check that we've done all our learning objectives. And we've already checked that we've explained the trend in reducing ability, and we've already listed out the products formed by reacting halides with sulfuric acid. And we have now explained why acidified silver nitrate is used to distinguish between the halides, because they're all colourless to start with, and they perform different precipitates, different coloured precipitates when you react them with silver nitrate, or in the case of fluoride, not a precipitate at all. So there we are. And we've analysed the trend in solubility of this silver halides in ammonia. So if you remember, the chloride is soluble in dilute ammonia, the bromide is soluble in concentrated ammonia, and the iodide is not soluble even in concentrated ammonia. And lastly, we wanted to prepare for the required practical 4, which we have done because that is the silver nitrate test. There we are. Thank you very much for listening and watching. I hope that's been clear for you.